So we talked about inner product spaces. Let V be an inner product space. We said that we can create a norm out of it. So there is a induced norm. And so there is a norm topology. I.e. open, so there's the open ball. Open sets, convergence, and completeness. Okay. Okay, so we're going to have a very important concept. The Hilbert space. So a complete inner product space is called Hilbert. Is that okay? The midterm, it will be restricted time. So we'll see. I have to connect with the, so let me say, I have to see what the international time zone students need. So I have to see how much time they need, and then I will do the same for you. But it would be restricted time, so maybe like, I don't know, restricted time. So the standard example is the RD with with the dot product, because we showed in chapter 1 that RD is complete with respect to okay. So that was in chapter 1. Okay. So now we're going to do a very involved example. Another example. That will take us most of the class. Is so L2 RD. These are all the functions on RD to R, such that the square integral is finite. So these are called square integrable functions. Okay. All right, yeah, this will be a very long proof. So actually, let me also give you the typed notes. So 1 second, let me upload it on the chat. All right. We'll show that square integrable functions, L2, is Hilbert, complete. Why do we care about this? So that says that if you take Cauchy limits of integrable functions, their limit is also L2. So yeah, that's quite important. You cannot have things so they're nice and integrable, and they remain so. So you have closure under limits. Yeah, that turns out to be very useful. Okay. I don't know. For example, no, it's fine. Okay. All right. So we start with Cauchy sequence. So I like this proof because we're gonna go over. So this proof will be a preview of many techniques from our second semester, from the next semester. So that's why I'm mainly doing it. We're gonna go over many of the basic ideas. We start with Cauchy sequence Fn in L2. What does that mean? For every epsilon, there exists n epsilon, so that for all m and n, f of n, f of m, L2, which is just the you know, the square is less than epsilon. Okay, so that's what we mean by Cauchy in this space. So there's a bunch of steps. So wait, is that okay? Steps. First, build candidate limit. So the proof is similar to what we did for continuous. Build candidate limit f in L2, f, such that you know, fn of x goes to f of x at least pointwise. And then show, we'll do it for a subsequence. Then show that the subsequence goes to f in L2, i.e., you know, goes to 0. And finally, upgrade that to the full sequence. So fn goes to f in L2. Okay? All right. So this is a very involved proof, but you'll see the main ideas for the whole semester. Okay. So our candidate is let f. Okay, so first pick a subsequence. Nk, f and k, such that fnk and fnk plus 1 in L2 is less than 1 over 2 to the k. I think this was in your homework, but the idea is a hint by diagonalization, meaning, you know, for epsilon 1 over 2, let fn 1 equal fn 1 half, you know, epsilon 1 over 4, fn 2, f1 over 4, and so on. In the Cauchy definition. Is that okay? Okay, so this is your sequence. Then let f of x to equal the following. So f of n1 x, and then the telescoping sum f and kx minus f and k. Okay. All right. And so this would be our limit. That's what we will show. We want to show f of nk goes to this guy in L2. So to do this, we will need a theorem. So theorem is called the monotone convergence theorem. So this one we will prove it the next semester. Okay, so suppose functions Gn are monotone, i.e., so yeah, first they're monotone. G1 is less than G2x, less than G3x, and so on. And also they converge pointwise. So Gn of x goes to G of x for each x. Okay. What's Cauchy definition? So, I mean, all right. What do you say? I mean, we wrote it here, right? So we said if you start with the Cauchy sequence, i.e., that's the guy. Is that right? Yeah. So this is the monotone convergence theorem for functions. And what it says is, so if you remember for real numbers, we had the same thing, right? So we had, if you remember for reals, it says if the real numbers increase, A1, A2, and you have bounded above, then there's a limit. Then integral of Gn of x dx converges to the integral of g of x. So that's a very powerful theorem that we use it all the time. So picture is, you have these g's, and they're bounded above by g. And that tells you that their integrals will converge to the integral of g. Does the function, yeah, they have to be positive. No negative. All right, so we're not going to prove this now. This is a lot of stuff. We're going to do it next semester, but we'll use it. Okay, so All right. Okay, so let Gn of x to equal, let me write like this. Let Gn of x be f n1x and k1 to n. Yeah, so yes. Right, so by the so by MCT, so since Gnx is less than Gn plus 1x, and you know, the pointwise limit is clear, so, and you know, Gn of x goes to G of x. We get the following, we get yeah, we get that the integrals also converge. Anyhow, yes, so G of x with absolute value is equal to, so we get by MCT limit of n to infinity of the integral of Gn of x you know, yeah, so we get this. Okay. So that's what we get. But then the question is, is integral of g squared x finite? Well, let's see. So, okay. So we will use the right-hand side. By a triangle inequality, what do we have? So again, we have g squared x limit, and then the L2 norm of Gn. But this guy is a sum. So it's Fn1, and then the sum up to n. Okay. Now use triangle inequality for norms. So we did this last week. And that tells you have the limit of Fn1 plus the limit of this subsequence. Okay. Now let's see. We had a very convenient definition assumption. Yeah, so we assumed, let's call this star, by double star, we get f of n1 plus the limit of what? Of the 1 over 2 to the k. Because this guy is less than this by construction. Okay, but what is that? This is f of n1 plus the infinite limit. And this is the geometric series. Yeah. Which is finite. Okay, so going back, that says that this guy is finite. But what is this guy? So we showed that the g of x defined as f of n1x x is in L2. But by triangle inequality, we similarly get that f of x, which is f of n1x let me do this carefully. So um, we get that this guy by triangle this guy is less than the than the L2 norm of this. So and so this is finite. So f is also in L2. Is that okay? Yeah, let me summarize what this happens. Summary. We showed so starting from we start with a subsequence that satisfies f and k less than 1 over 2 to the k, and then we showed that f okay, so then g, no, so we show that we have f here. We showed that this guy is in L2 by working with g, the absolute value of it. Okay. All right. So next, we show that that in fact f of nk goes to f in L2. So we haven't showed that yet. Is that okay? So here's another very powerful theorem you'll see in many places, like probability. So dominated convergence theorem. Um, so again, suppose the sequence of functions Hn satisfies two things. One is bounded above. So Hn of x is bounded above by some function. I don't know. You can call it whatever. B of x. And two converges pointwise. So Hn of x goes to h of x for each x. Again, the picture is you have this Hn, which can be negative now. And they don't have to be monotone either. So they can go any way they like. But there's a Bx bound top and bottom. It can be a function. So this is a function. So let me erase this. Yeah. Okay. So yeah, if you have two dominating functions, b of you have a dominating function b of x, then same statement holds as in MCT. So Hn of x. Well, there's many ways to write it, but that's one way. It goes to 0. Okay. Fine. Okay, so let's see. Okay. So we want to show that f of n minus f of x in L2, it goes to 0. Okay, but what is that? So f of x minus f of n. So we have f of n1 x This is a telescoping sum. So really you're left with starting from n plus 1 going to infinity. Okay. So we will denote this as, if you will, h of n. Yeah, let's just do that. So h of n. Is that okay? Fine. So we have our sequence. Then we need our bound, but you know, hn of x is less than by triangle. You know, the sum like this. Which is less than g of x from above, which we had shown that is L2. Okay, so by, so okay, we have this, we have this. So by dct, so by dct, we get that the integral of hn of x minus 0 goes to 0. Yeah, I doubt anybody's following, but I hope someone is following. I have the notes. I typed it and I would put more details. So this is just a preview, so I don't expect anyone to understand it too much. But at least to get some of the ideas like MCT and dominated convergence. Okay, so we showed that f of nk goes to f of x in L2. And finally, we upgrade to the full sequence. We upgrade to fn of x. So how do we do that? I.e., we want to show that fn of x minus f of x in L2 goes to 0. Okay. So as usual, I fix epsilon. There exists n epsilon. Such that, you know, fn minus fm in L2 is less than epsilon over 2. Then by the convergence above, there exists n tilde n epsilon over 2 bigger than n epsilon over 2, such that, you know, f and k minus f is less than epsilon over 2 for all nk bigger than that guy. Now we put them together. Usual triangle. this guy is less than epsilon over 2 by Cauchy. And this guy is epsilon over 2 by the convergence. And that's it. All right. If you have any questions, just put them in the chat room. We're going way too fast. Okay, so a remark, starting with any so why is this useful? One application is in Fourier series. Meaning, starting with f in L2, consider the its Fourier series. What is that? So f hat of x, other people write as s of x. This is the limit of the following. Make more space. So A0 up to n, K1, AK cosine of Kx, PK of sine Kx. AK is the inner product. So yeah, so this is in the notes. This guy is the f with 1, meaning 1 over 2 pi minus pi pi f of x dx. What is AK? AK is 2 times f of cosine of kt of kx. So these are the projections, the dot products with the standard basis. Now, a big problem with Fourier series is convergence. So we don't know if this limit convergence in what sense? L2, the supernorm, pointwise. So it's not always true. But using our, if AK, how do you say it? But if summation of AK square and pk squared is finite, then the function Sn of x is in L2. So by the above theorem, the limit exists, i.e. Sn, the Fourier series converges to f in L2. Is that okay? All right. Fine. Sure. So if you don't have any questions, I'll just do one example and that's it. Okay, so take for f of x, x squared with x in the minus 2, 2. We will compute its Fourier series. It's a bit of generalization, but we will use the, so very often we have different definitions. So we will use FG, what is it? 1 over 2 minus 2, 2 f of x, g of x. So in tests and finals, we will always tell you what inner product to use. So we will always specify the inner product. All right. So let's start computing the coefficients. Is that okay? All right. Okay, so we claim that, so let me at least do this claim and then we might finish it. Yeah, next week I don't think we have any classes. I will email you about it. Bn x squared sine, what is it, n pi x over 2 is 0. This is because for any odd function, what does that mean? F of x with a minus is equal to minus f of x. We always have minus L f of x is equal to 0. How to see this? Well, just split it. And do change of variables. All right, we run out of time, so I will continue, if not next week, in July. So I will stick around here for questions, but yeah, we're done class-wise. So I will stick around for questions, for comments. Will there be extra office hours before the exam? So let's see. Yeah, we should have some office hours. I will try to schedule something. Let's see, what else? Could you explain the F hat part? Sure. Right. So this guy is called the Fourier transform. And by definition is equal to the limit of the Fourier series. So, which is this guy. And so what did we do? Yeah, we used the above theorem. So we showed that that if your sequence, if this sequence is in L2, then and your Cauchy, which you can show this guy is Cauchy by telescoping. Yeah, so if you have this guy in L2, then we showed that the limit should exist, and we call it F hat. Actually, no. I shouldn't have written it as F hat. This is a bit, sorry, I made a mistake. This is not F hat. No, this is F. The coefficients are, sorry, my mistake. This guy is the Fourier transform. So F hat of K. Yeah, I shouldn't say too much about this but yeah, these are the Fourier transform. Oh no, I meant to write F. Okay, so how did you go from the limit of A0 and to the limit of, no, by definition, this is the, thank you. That's how we define this limit. This guy here is just this guy. Is that okay? Go. Is that okay? I have a question. Yes. So the question is, if you have two equivalent sequences, can you say that they have the same limit? And the answer is yes. Will we have all previous homework results before the midterm? We'll see. I mean, it's up to the TAs. I cannot force them to mark fast. So what can I say? We can use it, or we have to prove it. You know, like, this is not too much to prove. It's fine. You can do it. Yeah, that's one thing. You have to make sure they converge first. Absolutely. For example, AN equal to N 1 over N and Bn 1 over N, these go to infinity, but these guys are equivalent. Will we have normal all 8 office hours tomorrow for homework 5? Yeah, we will have office hours, definitely. But we will have even more next week. What else? All right. Anything else? You want me to wait? Say wait.